Hi everyone. My name is Keletso and today we'll be covering a section for Maths Paper 2 called Trigonometry. As you can imagine, we're on metric level, and we understand that some of the things that you might have done in grade 10 and 11 you might have forgotten. So the best way to start about this is to start doing revision. But the whole ideology of trigonometry revolves around triangles. Just the study of triangles, how they relate with each other, the angles and stuff like that. So yeah, this is why I have my triangle written down here. You take a look at this triangle. There exist angles on all the corners of this triangle. You have a 90-degree, you have another angle A represented by this. So there's the angle A, and then you have angle B, which you already know what it is. It's 90 degrees. And then we have angle C. So we'll just call it angle C for the sake of this context. So now, we also understand that if you want to find the sine of angle A, then we know the principle from grade 10, which is sol Cator. We already know this. And then we know that when it's sine, when you want to find the sine of whatever angle, we are going to say that it's opposite over hypotenuse. Same applies with the cosine of A, angle A. We know that it's adjacent over hypotenuse. And we also know that our tangent of A is given by opposite over adjacent. So now moving on, we also learned that about the Cartesian plane. So there's going to be our y-axis, while this is our x-axis. And then you have a line starting from the origin, going diagonally. And then you have this line over here. So this kind of resembles a triangle. And then here we have a certain value x and a certain value y. So now we have our angle theta here. Let's call it theta, which is an acute angle, for the sake of just understanding acute angle is an angle between 0 degrees and 90 degrees. So we know that any angle between this part is an acute angle, and we're going to use this as a reference quite a lot going forward. So, but when we have to use it, I'm going to come back to this and then reference it from here. So I'm just going to call this page number 2, then this one, just to make things easier for myself. So now, since we know that we want to find the x and the y in the context of our trigonometric ratios. So now we know that the sine of theta is equals to the opposite. So this line, these are opposite. These are opposite in the Cartesian plane. So we know that from here going up until here, it's this units, it's y units going up. So we know that we have our y here. And then the same thing applies here from this point till that point. We know that you've went x units to the side. So we already know that what our opposite is y. So those are opposite, y, over the hypotenuse. So let's call our hypotenuse r. Let's name it r. So it's going to be the sine of theta is equals to the opposite, which is our y, and the hypotenuse, which is our r. But now, what did I say? We want to find y. So when you want to find out y, we want to make it the subject of the formula. So you're just going to multiply by r on both sides so that we can get y is equals to r, the sine of theta, right? And then we want to get our x in the context of trigonometric ratios, just like we found our y. So we know that the cosine of theta is given by the adjacent over the hypotenuse. So now when you look at this Cartesian plane, we notice something. We notice that our adjacent, those are opposite, those are hypotenuse, and then x is our adjacent. So now we already found x. So it's adjacent over hypotenuse, which is r. And then now we do the same thing. We multiply by r on both sides. This cancels out that, just like this one's over here. And then we get x is equals to r cosine of theta. And then we can also go back, to our Cartesian plane and write it as such. So I'm just going to write this with a pen because I don't have so much space to write in with a marker. So I'm just going to say that our x is equals to r, the cosine of theta. And then our y is equals to the r sine of theta. Moving on from here, we can use those facts that you've developed here to get into what you probably learned since grade 7, which is the theorem of Pythagoras. But you want to express it in such a way that it's trigonometry friendly. So now we know that our theorem of Pythagoras is just r squared is equals to the x squared plus the y squared. But now, if you look, I'm just going to name this 3. If you look at what we got here for x, we got r, the cosine of theta, right? You got r is a cosine of theta. And then now the other thing that I just want to mention right now is that if we let's say before we start with this one, we let r is equals to 1. Just to make things easier for ourselves, we let r is equals to 1. So that 1 is equals to x squared plus y squared. So now we want to focus on the x components and the y components. So now we know that when we get here, given that r is equals to 1, we have our x as x is equals to 1 times the cosine of theta, which is just equals to the cosine of theta. And the same thing applies when it comes to y. Y, we found it to be r, the sine of theta. But now we know that r is equals to 1. So you're going to have it as 1 times the sine of theta, which is just equals to the sine of y, of theta, sorry. So now we want to substitute this facts here to our theorem of Pythagoras. So now we know that 1 squared is equals to 1 squared is equals to our x here is equals to the cosine of theta. But this x is squared, so you're going to square it, and then this y is also squared. So, but our y, we found it to be the sine of theta, so it's going to be the sine of theta squared. So now, removing the brackets, we find that the cos square of theta plus the sine square of theta is our answer. But this is all equals to 1. And this leads us to the first trigonometric identity. Trigonometric identity. And we're going to use this identity to find even more identities going forward. So now we go further. So we can also, we can kind of play around with this thing. We can play around with it. So now we can say that, okay, the sine squared of theta is just equals to 1. And then we transpose this to the other side, we get minus cos squared of theta. And then if we divide both sides by the cos squared of theta, even for this one, cos squared of theta, we find that, okay, I'm just going to say that the sine, just for simplicity's sake, over the cos theta all squared. I hope that you can all agree with that. And then this is just going to be 1 over the cos squared of theta minus cos squared of theta over the cos squared of theta. So I'm going to move, it continues on the next page. Just going to quickly move on to the next page. So we know that if you just look at this again, we know that our sine theta over the cos theta is just equals to the tan of theta. If you didn't know that, now you know that the sine of theta over the cos of theta is just equals to the tan of theta. So our tan of theta, but this tan of theta is squared, so we're going to square it. And then now we also know that this, I'm just going to keep it simple and move at everything one step at a time. We also know that 1 over the cos squared of theta is the same as this. But then now we know that this, the cos squared of theta over the cos squared of theta is just equals to 1. So you know that it's minus 1 now. It's minus 1 because of the fact that this is just going to cross divide, and then it gives us 1. So now we know that 1 over the cos of theta by one of the rules that you've learned in trigonometry is equals to the sec of theta. And this is all squared minus 1. And then we know that the tan, if you remove the brackets, is going to be the tan squared of theta is equals to the sec squared of theta minus 1. I hope that we are all in sync when it comes to this. This is just to play around with the idea of, the trigonometric identity. So there's also another trigonometric identity, the trig identity, that we'll use on some of the problems going forward that you're going to find in the context of trigonometry. And then now, how can we also play with this? The other thing before I continue is that we need to pay attention to some of the special, some of the rules with regards to algebra. We know that, for example, when it comes to the sine, if you write the tan of theta is equals to the sine of theta over the cos of theta, we know that for this to be possible, cosine of theta can't be equals to 0, because any number divided by 0 is impossible. So that is just the side note going forward. So now, already you found 2 trigonometric identities. So going forward, I just want us to find this trigonometric identity as we go into problems. But now the other thing that really I just want to emphasize before we start with the actual grade 12 content is the cast. So the cast is basically just an aid to show us where the trigonometric ratios are positive and negative. So we all know that this stands for all. I'll assume that you all know that it stands for all. So all stands for all trig ratios. I'll just say all trig ratios are positive. I'm just going to put plus here. And then here we know that sine is positive, and then tan is positive, and then cos is also positive. So now if you get things like problems that such as sine of 180 degrees plus theta. So now we go back into our aid and say that, okay, no, this angle, né? So the theta, guys, just before I continue, the theta, it should always, okay, I'm going to put NV here, not a Bella, that theta must always be an acute angle. Always be an acute angle. So I'm just going to go back to the definition that I gave for an acute angle when I began this lesson. So I gave that an acute angle is an angle between 0 and 90 degrees. It's an angle between 0 and 90 degrees. So it's an angle from just above 0 up until just below 90 degrees. So now, we know, if having this as a fact that it should always be an acute angle, we know that this lies in the third quadrant. And then I'm just going to show you guys reference. We're going to use a lot of reference in this lesson. So now we know that here it's, okay, I'm just going to start here 0. And then here it's 90 degrees. And then here it's 180 degrees. And then here it's 270 degrees. And then here we also have 360 degrees. So now, if we take 180 degrees and we add with an acute angle, we know that it's not going to surpass this point of 270. So we are sure that this lies in the third quadrant, where tan is positive and all the other trigonometric ratios are negative. So in this context, we are dealing with sine. So if we're dealing with sine, you know that sine is negative in the third quadrant. It's negative in the third quadrant. So now we know that our answer is just going to be the sine. Okay, I'm just going to neatly write it down so that the sine of 180 plus theta is equals to minus sine of theta. So those, we call this a method, just the method of reduction or the reduction formula or whatever. So I'm just going to just put this, the method of reduction, method of reduction. So essentially, that's how you can go about solving the other reduction formulas, really. So I'm just quickly going to move on to this, onto the other point of the lesson, where we really just get to talk about special angles. You know, so there'll be questions that you get into trigonometry where you're not allowed to use a calculator. So now, in this context, when you're not allowed to use the calculator, you need to find ways of working towards your answer without an aid of a calculator. So I'm just quickly going to refer. So we have a triangle like this. And then, okay, just before I start, let me just highlight on the special angles that we have in trigonometry. Special angles. So we have them as 30 degrees, 45 degrees, 60 degrees, and 90 degrees are all part of our special angles in trigonometry. The angles that we know, we must know, we are bound to know without the use of a calculator. So now say here we have 30 degrees. And here usually you have 90, and then you know that the sum of all the corners or all the angles of the triangle sums up until 180 degrees. So it's going to be 180 degrees minus 30 minus 90 to get this angle. So if we say that it's going to be 150 if we minus 30, and then it's going to be around about 60 degrees. It's going to be 60 degrees. So we have it as this angle over here. So now if you want to find the sine of 30, the sine of 30 degrees, we know that our sine of 30 degrees from, if we can just refer back to what you learned in grade 10 and 12, we know that our sine of 30 degrees is just 1/2. But we know that it's opposite over hypotenuse. So we know that our hypotenuse is 2 and our opposite is 1. And then if you want to find the sine of 60, we know that the sine of 60 degrees, it's still opposite over hypotenuse. So it's going to be, from what you learned, it's going to be 3/2. Because now if we use the theorem of Pythagoras here to find the side, we're going to find it as the square root of 3. Hence this answer here. So we're going to find it as such. So there's one of our special triangles. Let me just call it here triangles. And then the other special triangle that we have in trigonometry and always going to refer back to is the 45-degree one. 45. And then you have 45 here, 45 degree, 45 degree. And then here we have an angle of 90 degrees. So the summation of those should give us 180 degrees. So now we're going to have it like that, and then like this. And then we know, some of us already know from analytical geometry that, we use this line quite a lot. And that's why it's important to just know all this chapter so that you can use the knowledge that you got from the other chapter to the other chapter. So you know that tan of 45 degrees is just equals to 1. But 1 can also be written as 1/1. So you already have an idea that, okay, now let's go back to solve part 1. So I'm just going to write it here so that it can be a bit faster. So we know that opposite over, it's tan is the trigonometric ratio of tan is given by opposite over adjacent. So now we know that from this, if we use this as our reference, our opposite is this one. And then the opposite is 1. So you put it here. And then our adjacent is also equals to 1. And then if we use the theorem of Pythagoras, we're going to get the square root of 2 here. So you're going to refer to this quite a lot. So right now we're just trying to see what we're going to need. So now going back to the theorem of Pythagoras in the context of trigonometry, we know that, and when r is equals to 1, we know that it is equals to the trigonometric identity, the sine square root theta plus the cos square root theta is just equals to 1. And then if you want to find, for example, if you want to find the sine square root theta, obviously we transpose to the other side. So when you transpose to the other side, it's just equals to 1 minus the cosine squared of theta. And is this going to be equals to 1? At the sine of theta, if we take the square root here and take the square root here, the sine square of theta is going to be plus minus 1 minus cos square of theta. The same applies with the cos. So cos theta, as you can imagine, is just going to be 1 minus the sine square of theta. So now, I think we have enough tools to be able to solve our first trigonometric related problem. So now I'm just going to quickly write it down so that you can solve it. I'll just say it's an example. So now, if you have the cosine of 420 degrees, and then we have minus the sine of 225, But this 200, the sine of 225 is multiplied by the cos of minus 45 over the tangent of 315. So now we are going to solve this expression without using a calculator. So I'm just going to say without using calculator, determine the value. And is that determine the value. So now, if you don't use a calculator, the first and the only resort you can go into is to write these angles in such a way that they're written in a special form so that they can be easier to solve. So now we know that 420, if we are to write it in a reduction formula sense, it would be something like the cosine of 360 degrees plus an acute angle of 60 degrees. Because an acute angle is an angle between 0 and 90 degrees. And the angle that we should always add here should be an acute angle. So now we continue and say that, okay, sine, how can we write sine? We write sine as 108 degrees plus 45 degrees, which just gives us 225. So it's 180 plus 45. So I'm just going to just go onto another line right in this, saying that this part is full. And then plus, so you're going to leave it, this one is written, it's not written in an acute angle because minus 45. Do note this, minus 45 is not an acute angle because it doesn't fall within the range of 0 and 90 degrees. So you can just write it like this, which one really make a difference, 0 degrees minus 45 degrees. So all this, you must divide it by the tangent of, but okay, we see that we can also express this in terms of a reduction formula. So now, if we take 360, for example, and minus it by 45, an acute angle, which is also a special angle of 45, it gives us 315. And then now, as you can imagine, these angles are all special angles that I've written, so it's going to be easy now to solve this problem. So now we know that if we reduce this, we know that 360 degrees plus 60, because 360 degrees is a revolution around that Cartesian plane, or a circle rather. So we're going to fall in. I'm just going to quickly refer us back to just show us that we've done this at some point. Just give me a moment. Just give me a moment. So yeah, we know that all the trigonometric ratios in the first quadrant, which is just the cosine of 60, are positive. So cos, this is just going to be cos of sine of 60 degrees plus, and then we know that this falls in the third quadrant where the tan is only tan is positive. So now we know that the sign is going to be negative. So I'm just quickly going to cancel this out and then write minus the sine of 45. And the same applies to this one falls, because now you add 0. If you minus 45 degrees, we know that the cosine is positive here. So you're going to have the cosine of 45 degrees. And then we also do know that the tangent of 360 minus 45 is on the fourth quadrant where tan is negative, so you're going to have minus tan of 45. So now we already know all this works from this. I'm just going to quickly refer back to this, maybe. I think, okay, it's only, but okay. If you refer back to this, yeah, we know that the cosine of 60 is opposite over hypotenuse. So it's just going to be 3/2 minus the sine of 35. And then the sine of 45 is just going to be, let me just find this, sorry about the weight. Excuse me with the weight. So yeah, I'm just going to refer to those two papers. The sine of 45 degrees. So the sine of 45 degrees is just going to be opposite over hypotenuse, which is just 1 over square root of 2. And then the cosine of 45 is just opposite. The cosine is actually adjacent over hypotenuse. So it's just going to be 1/2 again. 1/2. And then the tan of 35 effect from analytical geometry is that it's equals to -1. And that part you simplify and then get your answer. So